My name is Greg Casey. I'm from Dell Computers, and I'm here representing Gen Z, which is a consortium. As we just discussed, what is Gen Z? As everyone knows, the data is exploding. We have all kinds of devices. Some people are estimating 50 billion IoT devices, 180 zettabytes of data. Of course, this is marketing people talking, so God only knows if it's true. But all the companies are, how are we going to monetize this through all the different things that we've been talking about, you know, machine learning, deep learning, and all those kinds of things that are heavy into memory aspects. So the big question is how do the processors get that data in a quick manner? Over the years, the problem is becoming the cores and the memory. What's the bandwidth to those things? And as you see from this diagram, the number of cores is going up astronomically. Intel and AMD and IBM and Cavium are all coming up with multi-cores. The problem is the number of pins on the devices is growing. As even done motherboards, they know 4,000 pins is what we're talking. And it's a lot of pins, 8 memory channels. Trying to fit 8 memory channels into something is very difficult at 300 plus pins per channel. I saw one of the boxes out there that has DIMMs on both sides. Very creative, very creative. But that just illustrates the problem. PCIe, Gen 4, the speeds of it, and then Gen 5 in another 18 months, let's say. You know, over time, the memory bandwidth per core has been going down, not going up. We had a little bump when we took the number of channels from 6 to 8, but it's still per core, the bandwidth is going down. We also have the problem of memory, the kinds of memory. To the far left, you see processor, SRAM, and on the far right, you have tape. Not much tape anymore, but it does illustrate the point that we do have flash. We do have rotating devices out there in that file area. But then we have new kinds of memories coming in. You know, SRAMs, DRAMs that are sitting on the processor board, volatile. You have persistence on the right. But then we have this new thing we're calling storage class memory. And there's a preponderance of different kinds of storage class memories coming up, very persistent, and all the problems associated with that. So as we go forward, the pyramid diagrams try to show over time that we will see more persistent memory and less of the other. So our solution from the Gen Z perspective is to put a fabric in between the processor and the memory. It addresses the problem of this rise of microsecond devices, as marketing people call. We're getting away from the block I/O concept. These are read-write memory devices because we're talking to the processor directly. Memory fabric allows us to add these storage class memories asynchronous to the processor releases, where we don't have to wait for a processor. We have some kind of universal bus that we can talk to in between the releases. It also, with a fabric there, we can have what we call a memory-centric architecture. As opposed to having the CPUs in the middle, we'll have the memory in the middle, and everyone can come to that table and access that common memory. Main motivation of that is you don't have to copy the problem from one location to another, and we do a lot of that in all of our problems. Another thing is disaggregation and composability. We have made a lot of attempts at Dell and across the industry to decompose our servers, make them modular. One thing we haven't been able to bust apart, and I know a lot of people in this room have the same problem, you can't bust apart that CPU and that memory. One of the concepts, one of the driving motivations here is to do exactly that. This is a marketing diagram, but it shows kind of the concept of what we want. We want to be compute agnostic. We want to increase the bandwidth for those things. Probably never getting up to the point of DRAM. You're going to pay a certain amount of penalty to go through a fabric switch, but still keep very high performance. Low latency, if you're talking about load store, you have to have low latency. And we want to open it up to innovation. That's why this is an open consortium. Like I said before, I'm not representing Dell here. I'm representing the Gen Z. We want to have many vendors come to this in 4 to 5 years and play into this infrastructure. High availability. We can't have machine checks dumping the whole machine. We have to have ways of getting around that and making it happen in high availability. Security is also. If you have multiple CPUs hitting the same memory, you want to have ways to protect it either by region or by volumes. Another way to look at it is high performance, low latency. These are performance goals. We want it reliable, flexible, secure, compatible, and economical. What we're showing here is this fabric that sits in the middle, which would be a switching fabric, and each one of these devices would be generating Gen Z packets. So if you think of it in a very simplistic way, a CPU talks to memory. It talks to that with an address and data. If you back up just a step, the concept of Gen Z is we packetize that. We put the address in a packet, we ship it across to a destination. That destination, which we call a component, that component unrolls it, takes the address, does all the security checks on it, and then retrieves that information from memory, puts it back into a packet, and shoves it across. And we all know enough about networking that doing that, you're able to have multiple people talk to it and have your system grow and those kinds of things over time. This is a marketing type of slide, but the goal here, and what we're trying to show is, just kind of an important concept, is in most traditional ways we have all kinds of file systems. We have I/O buffers, we have drivers, we have a controller sitting out on that NIC card or that storage card. Our goal is just to have no copies, and it happens just on one pass. So even though we might introduce a slight latency and a slight bandwidth impact, the overall problem, if we can go from 2,000 or 3,000 instructions to get something to happen to no instructions to happen, that's the whole motivation here. Gen Z has taken on upon itself, we have the protocol stack and we also have the PHY stack. And what the motivation of this slide is we're saying we have multiple lanes, just like PCIe. But different than PCIe, we also have scalable. We can have 2 lanes going one way and 6 coming the other way, so it's negotiable on the number of lanes, so it's not necessarily symmetric. The speeds, we have 32 virtual channels in the definition. We have, like I said, security, multipath. Our goal is in the 50 to 100 nanoseconds across. We talked earlier about composability. And what we mean here is by taking all these modules that have a common interface, which we call Gen Z, and be able to assemble them into different things. Compute modules, memory storage modules, actual storage modules as opposed to memory. And Gen Z also has the concept of many instructions for sharing and commanding data across the bus. So it's not just memory accesses, it's CPU to CPU, CPU to GPU, aggregation, and those kinds of things. We've conceptualized different kinds of topologies we could put together. The simplest, of course, is we do have the concept of daisy chaining, where you can have one DIMM and that DIMM rebroadcasts around, and that's kind of what that first picture shows us. In the second bullet of that, we talk a little bit about that we have 2 kinds of PHYs. We have both an 802.3 PHY, your basic Ethernet type PHY, or we have the PCIe PHY. And the reason we have 2 is because Ethernet PHYs tend to be more silicon hungry, more power hungry than a PCIe PHY. And a lot of our processor brethren really would rather put a whole lot of PCIe PHYs down as opposed to Ethernet PHYs. But when we get to the edge of that processor board, we want to go across a mid-plane across to another chassis. The Ethernet PHYs really perform better. So that's why we have this dual PHY philosophy. We also have, besides just the daisy chain, we have full meshes and torus type interconnects. And we do have the concept of a Gen Z type switch in the middle where we could interconnect many things. The consortium, and I haven't talked about the members of the consortium. There's about 40 or 50 companies right now. It's very dynamic. And at the last slide, I have a whole list of that. But we've also taken on the connectorization. Because if we're going to have this infrastructure where we have to have things connect and be uniformly connected between things, we had to define a common connector. We went out on a search and we have selected a connector, and it comes in what we call 1C, 2C, and 4C. Chiclets, what the C stands for. But the reason we didn't say by 16 or by 8 was because of this non-symmetric upstream, downstream communication. So a 1 by is 4, by 2 is 8, by 4 is 16. We also have cable solutions, so we can do that as well. Yes, question, go ahead.
Are they 16 in each direction?
Yes, absolutely.
So it's really 32.
Yes, it's 32 SerDes if you want to look at it from that direction. Yes, absolutely. We always, as an industry, get that confused, but no. I always like to think about it in one direction. Besides, another note on that OCP 3.0 NIC uses this same exact connector. We did some of the legwork. We had that okayed by, submitted to SFF. And so OCP is one of the people that's taking a look at it as well. And I think it is part of the connector scheme for the OCP 3.0. We're looking at scalable form factors where we can have processor modules, GPU modules, FPGA modules, memory modules, disk type SSD modules, and come up with some standard common form factors that we can use across the industry. This is still ongoing. We still haven't come out to the precise definitions yet, but our working group is continually working on this. Because those form factors are further out, we are looking at entertaining what we call PECFF, Common Form Factor for PCIe. Probably intercepted the Gen 5 timeframe. And if anyone's familiar with the PCIe board, typically you have your connector sitting at this end, which is fine for some things, but sure is awful for a server because our processor's way over here and we gotta go way down here and come all the way back. So we did not like that. We want to figure out a way. The only thing it does allow you to do is have variable length PCI boards. So that's the real advantage of it. So our concept is we have a by 16 sitting here, right here, excuse me. And so if we want to go to a by 32, we could put it here. So you have two connectors. Also, we're entertaining how to deliver high voltage to it, 48 volts and higher power as well. So we have this concept of a growing board that would still fit into a standard form factor for a PCIe type board. We're looking at scalable form factors. At Supercomputer, we had some modules, 3D printed modules to illustrate these concepts. Your imagination can go wild on this, how you could interconnect, how you could do it. We wanted to have some kinds of examples to show, so that we had a drawer pluggable and we had a 2U type server as well. This slide illustrates that we also are talking about storage, how to do real storage across this as well. We can also do communications across it. There is messaging capabilities within the Gen Z spec. So it can be used for other things than just a load store. Our main focus is load store, but there are other attributes to the protocol. So I think I've hit all these bullets, but we'll go through and make sure. We can support up to a 64-bit address, which should keep us good for a couple more years at least, I hope. That's a lot of memory. It illustrates some of the advanced operations we have, get puts, collectives, those kinds of operations that are part of the protocol. And as I said earlier, we have 32 virtual channels. We have different traffic classes. Wanted to illustrate the number of people that are already in the consortium. We have processor companies. We have large system companies. We have I/O companies. We have connector companies. We have software companies. We have IP companies. Most important thing is we were launched in 2016 to create an open standard. There are some 50 members now. We've released our core spec, which is the protocol spec. We released that last month. We have a scalable interconnect, which has been released. That's the one that's been adopted by OCP. Also, it was donated to SFF. We have a version of the 8639 for, we like to call it legacy. I know that's new for a lot of people, but that's a legacy to us. And so I guess this is an old slide. We were at Supercomputer 17. We will be at 2018 as well. So what's going on this year? We'll continue our efforts to create Gen Z IP and in silicon. We have several companies that are doing it. Consortium works with a group to do compliance, mechanical, PHY, software, other stuff. And so we're going to be at the ISC show in Europe, Flash Memory Summit. We hope there's no fires there this year, because that was terrible last year. And again, it's Supercomputer, I guess it's in Denver. We want to have real development systems by the end of this year. Early adopters targeted for 2019, 2020. And paid advertisers, we're interested in new members too. So please get involved. Now, what time is it? 21. I got time for questions. I kind of raced through that. Yes?
I have a question around the compute, memory, and storage class memory, and its applicability for Gen Z, given that Intel has a lion's share of the CPU market, and you know where I'm going with this question.
Yes.
Out from CPU to DRAM to 3D XPoint now.
Yes.
So do you have any strategies on how to break through and have Gen Z increase adoption in that kind of environment where?
I can answer your question in two ways. One that I can't tell you, because there are things happening behind the scenes. Dancing. But work and conversations are going for a more direct connection. We do have PCIe bridges that we can map into that, and so work is actively going there. So there's two different directions we're going on that. We would love to have them as a member company. So, other questions? Yes.
When do you think Gen Z switches will be available?
I can't talk to the companies that are actively developing when they're going to come out, but I would say in the 2020 timeframe. They might be pushing into 2019, but that's awful quick for a product because these are hard silicon and that kind of stuff. So we have FPGA codes doing switching now, but FPGA is a far cry at 4 channels by 4 to a real switch at 198 SerDes or something. It's a significant piece of switch hardware. Yes?
So besides disaggregating the memory portion of the
Yep.
Can you elaborate how moving to Gen Z will increase the amount of memory bandwidth per core? Because core count is going to keep increasing. It's hard to have a serial link scale accordingly in that
Yep.
space.
Yep. We don't anticipate that the DRAM will go away. The DDR buses will probably stay. And we expect that we'll have some repurposed PCIe lanes that we'll be able to take advantage of for memory traffic as well. So you're absolutely right. The speeds compared to, there's a good trade-off if you do trade off a DDR channel for a Gen Z, but DDR is pretty fast as well. So it's wide. That's why it gets. But we're almost to the mechanical problem of placing 8 DIMMs around a processor is really hard, and it's not going to get any easier as we go to DDR4, DDR5. We're still talking. There is some discussion about a DDIMM or differential DIMM, which might alleviate some of the pain, but if they stay single-ended, it's going to be very painful to do the SI problem there. Yes?
Does it support cache coherency?
Yes, we have a full chapter in our spec on cache coherency. There's another group called C6, CCIX, which they did a lot of work on that area. We have consulted with them. We have all the atomics, I want to call them, the basic building blocks that you can do a cache coherent. The assemblage of that into a actual interface is some work yet to be done. Yeah.
Higher level.
Yeah, you have to assemble that, and it'll probably be different for this processor versus that processor, those kinds of things. So, but all the atomics, and I would welcome our spec at genzconsortium.org is open. Feel free to go out and read it, and particularly if you want to read about the cache coherency part. Yes?
So I'm kind of new to this. So people who are in this field probably know about this already. So we talked about Gen Z, OpenCAPI, PCX, of course PCIe Gen 5. Why do we have these different protocols? Why can't we merge them together, make life easy for everybody?
Make it easier for me too. You're absolutely right. I'm heavily involved in the PCIe SIG. I'm on the board as a matter of fact. And at Dell we have done several PCIe based switched appliances or products. The problem that you have is, and a lot of people can attest to that, is when a PCI bus has to discover everything and make homes for everything as it boots up. And if you have to reconfigure that, it's rather painful. And some people have come up with some elegant software to reconfigure it, but generally it's a boot up kind of situation. Gen Z's concept is that you'd be able to add and subtract things dynamically. So you got an infrastructure of PCIe that was based on PCI. A lot of the infrastructure, we've added chapter after chapter over the years, but at some point that legacy is probably not going to be adequate. So, and it doesn't have the robust commands that you'd really want to pass across. So that's the reason for PCIe. The question about OpenCAPI, the question about C6, I think their goals are similar. C6, I believe, rides more or less on the PCIe structure, so it has some of the same limitations PCIe does. OpenCAPI I'm not as familiar with, but I still think it's a point-to-point bus as opposed to an addressable bus. I believe, I probably have some IBM people here, or OpenCAPI people that can tell me where I'm wrong, but I believe it's still a point-to-point. Basically, they're sending the address across and getting data back. It's not switchable. They can probably add some things to make it switchable, but at this point, I don't think it is. So those are the reasons. I would love to have them all come together. Questions for anybody else? Okay. Well, thank you very much for your time.